All right, everybody's here. Let's get this tutorial. I have three problem set. I'm going to demonstrate how to solve these problems. Tomorrow, I will give you the problem. You're going to solve it. Today, I'm going to go through step by step how we calculate some of this problem for anaerobic digestion process. Tomorrow, we'll give you a couple of problems so you can work out. Okay. All right. The first tutorial is go to the next slide. Make it full screen. So the question here is how much methane gas can be generated through complete anaerobic digestion of 1 kilogram of COD at standard temperature and pressure. Okay, how are you going to calculate that? Okay, hit the next slide button. So step one calculation is you're going to calculation of COD equivalent of methane gas. Okay, so for one methane to oxidize, how many oxygen you need? You need 2 oxygen. Okay, that will convert methane to CO2 and water. Okay, so the methane has 16 molar. Okay, so that's, you put the 16 for methane molar. Okay, oxygen has 32 molar, so you need 2 oxygen, so that'll be 64 molar equivalent. Okay, so you need 16 gram of methane and 64 gram of oxygen. That's your COD value. Okay, so for one methane equivalent to 64 gram of oxygen COD. That makes sense. So we're going with molar to molar. So when you have 1 gram of methane, so that'll be 64 divided by 16. That will give you 4 gram of COD. That makes sense? Okay. So step 2, you're going to convert methane mass equivalent to volume. Okay. So based on the ideal gas law, 1 mole of any gas at standard temperature and pressure occupies a volume of 22.4 liter. All right. So when you have 1 molar of gas, it simply equals to 22.4 liter of gas. Okay. So when you have 16 gram of methane equals to 22.4 liter of methane gas. So 1 gram of methane equals to 22.4 divided by 16. You get 1.4 liter of methane. So far you are with me? Okay, calculating how your molar equivalent or COD equivalent. Okay, all right, next step. So in step 3, you're going to calculate methane generation rate per unit of COD removed. Okay, so if you look at the equation 1 and 2, you can get all this in the thing in the below, right? So 1 gram of methane equal to 4 gram of COD equal to 1.4 liter of methane, right? So when you have 4 gram of COD, you have 1.4 liter of methane, and 1 gram of COD equals 1.4 divided by 4 equals 0.35 liter of methane gas. Okay, so 1 kilogram of COD equal to 0.35 cubic meter of methane gas. So complete anaerobic degradation of 1 kilogram of COD will produce 0.35 cubic meter of methane at STP, standard temperature and pressure, right? So that's a simple way of calculating how much COD you have in your input, how much methane you're going to produce. So when you have 1 kilogram of COD, theoretically how much methane you're going to produce. A simple way to calculate. Okay. All right. So let's go back step by step. Go back one more time to reinforce. Go back to step one. So that's a simple question, all right? We are trying to find out how much methane gas can be generated through complete anaerobic degradation of 1 kilogram COD. So we're doing 3 steps. Okay, first step, we are calculating COD equivalency of methane. Second step, you are conversion of methane mass to equivalent volume. Okay, so I'm going through step by step how we did that, because I need to know molar. Methane is 16 molar, oxygen is 32. There are 2 oxygen. We got 64, and then we convert them to finally get 1 gram of methane will give you 4 gram equivalent of COD. That's how you calculate COD equivalent. Okay, and then the second step again to re-emphasize. The STP, it's a general chemistry that 1 mole of any gas will equal to 22.4 liter of methane, which is the volume we are talking about at standard temperature and pressure. Okay. So when you have 16 gram of methane in the first step, so 16 gram of methane is 22.4 liter. So for 1 gram, 22.4 divided by 16, you get 1.4 liter methane. Next step. So we're now giving all this information from step 1 to step 1 and step 2. Now you can calculate a complete degradation of 1 kilogram of COD will produce 0.35 cubic meter of gas. So that's the way to calculate. So if you have any substrate, you have to calculate how to have COD equivalent. If you follow this rule, you can simply calculate that. Okay? All right. Any question on that? So let's go to the second problem. So here we are using a upflow anaerobic sludge blanket reactor. Okay, and this reactor in a scenario is treating food processing waste at 20 degrees centigrade. The flow rate is 2 cubic meter per day with a mean soluble COD of 7,000 milligram per liter. I want you to calculate the maximum methane generation rate in cubic meter per day. What would be the biogas generation rate at 85% COD removal efficiency? If your bioreactor, you're not going to 100% removal efficiency. I'm giving 85% your reactor removes your COD, and 10% of the removed COD is used to make biomass. So you only have 75% used for your methane conversion. The mean methane content of your biogas is 80%, right? If the wastewater contains 2 gram of sulfate, now sulfate reducing bacteria are going to compete for the same carbon substrate, right? How much methane could be generated? Again, it's a little convoluted. I'm throwing you a lot of numbers here, okay? I'll solve it for you very simply, okay? So you kind of picture this question in your mind. You have any doubt what we are trying to do here? You're okay so far? Okay. So what, again, you're saying that these are the scenarios when you go work in a company or work in big systems, you got to calculate. You got to figure it out. Okay, input of this much COD you're putting in a digester. The efficiency of digester, 85% removal of COD, right? 10% of that is going to make more salt. And then how much methane you're going to produce theoretically. And in the scenario, if you have a sulfate in your waste stream, then the sulfur reducing bacteria are going to compete with your carbon. How much methane will be reduced in the presence of sulfate and the activity of sulfur reducing bacteria competing with same substrate by methanogenic bacteria. So that's what this question is, okay? Now let's try to solve this question. Let's go next step. All right. The solution, the maximum methane generation rate, the complete degradation of organic matter in the waste could only lead to maximum methane generation and is also regarded as theoretical methane generation rate. Okay, so when you understand the degradation is complete, organic matter is, there is no metabolites, right? And it's not, some of those are still in fatty acid form. You are assuming everything is in completed to methane. Okay, so in that scenario, the waste could be lead to maximum methane generation, and we call that theoretical methane generation rate. So we are assuming everything is converted to methane. Okay, all right. Next step. All right, let's now put this puzzle, solve this. Okay, so we have total COD removed. So if you look at the question, we have 7,000 is your input, and is the cubic meter 10 to the 6, and you divide by 10 to the 3. You multiply by 2 kilogram per day, right? So if you are confused, go back and read the problem. Go back one more step, where this number come from. All right, so we have 7,000 milligram per liter COD, right? Then you have the cubic meter per day, and you have 85% COD, and then you have 2 grams of sulfate, all that in there. That's what the input in your equation is. Go back to the next slide. It's okay. So that's where you're inputting total COD removed, okay? When you calculate that, you're going to get 14 kilogram of COD per day. Which one? That's cubic meter calculation. Yeah, unit conversion. So from equation 3, in example 1, we have 1 kilogram COD going to produce 0.35 cubic meter of methane, the first problem, right? We already have solved that problem. So for 14 kilogram COD produces, if you already know 14 kilogram COD, produces 0.35 times 14, you're going to produce 4.9 cubic meter of COD per day at standard pressure. But in the problem, the temperature is 20 degrees. Okay, so now we have to calculate that. Okay, at 20 degrees, the methane gas generation is 4.9 times 293 divided by 2. I'm going to tell you how to convert your STP to 20 degrees centigrade. Okay, so that's where this number comes from. So go back to the my Word document. I'm going to show you how to convert from STP. Okay, go scroll down to the second page. Scroll down. No, go up, go up. Up, up. All right, up. All right, here we go. So a little down, get to the first paragraph. No. Move to the top all the way. Yeah. All right, here it is. The ratio of 293 to 273 is used in methane heat conversion for 20 degrees centigrade to account for the difference in molar volume at 20 degrees centigrade. The problem says you're operating your reactor at 20 degrees centigrade. So that's where your 293 Kelvin comes into that. The K is for Kelvin. So to calculate that for 20 degrees, you have to use this 293 divided by 273 for STP, right? That makes sense? Oh, it's not visible? The letter is too small. I mean, all I'm saying is this is standard rule how to convert your STP to the operating temperature. Okay? So you want to enlarge that and make it bigger. Oh yeah, that's really big. Yeah. Okay, now if you scroll up, you can tell how to convert the STP to the operating temperature of 20 degrees centigrade. Okay, so basically you get that number 293 divided by 273 to convert your operating temperature, your operation from STP calculation. That's what this number comes from. Okay, all right. Let's go back to your the problem PowerPoint slide again. Yeah. All right. Next slide. Make it big. Make it bigger. Full slide. All right. So that's not that full slide. Full screen. Full screen. Full screen. So yeah, this is what we put that. So we got this 4.9 cubic meter at 20 degree. We're going to do 4.9 divide times 293 slash 273 to get your 20 degree centigrade operating temperature. If you plug in that, you get 5.3 cubic meter per day. Okay? All right. So the maximum methane generation rate is 5.3 cubic meter per day. Right? So far you're with me, right? All right, move on to the next slide. Okay. So biogas generation rate. Not all COD is completely degraded. The fate of COD during anaerobic treatment process can be viewed as some of the COD is left in the effluent, not 100% converted. COD is converted to methane gas. COD is converted to biomass. 10% we already gave in the problem is converted to biomass. COD utilized if there is sulfate reduction, some of the COD is used. Okay, so those are some variables that you need to take into account. Okay, so now total COD removed is going back to the same calculation. You get this 11.9 kilogram per day. Okay, now go to the next slide. So as 10% of the COD is used to make more bacteria, more biomass, right? So only have 75% is now used for your methane production, okay? So remaining 90% removed COD has been converted to methane gas, okay? So COD utilization for methane generation is 11.9 times 0.9, which is 90%. 10% goes to biomass, right? So if you do that, your methane will be 10.75 kilogram per day. Okay? All right. So from equation 3, in example 1, we have 1 kilogram COD produce 0.35 cubic meter of methane at STP. At 10.7 COD produces 0.35 times 10.71 will produce 3.75 cubic meter methane per day at standard STP. Okay? All right. So at 20 degrees, again, you plug in 293 for 273, divide by 273 for 20 degree operation, you get 4.02 cubic meter per day methane. Okay? So what we are doing here is taking the 10% out for biomass production. It's not going to methane production. Recalculating how much methane is produced. That's all we're doing. Okay? It's the same number, nothing. Instead of 100%, we're putting 90%. That's all we're doing. I want to confuse you guys. Okay? So when you do that, you're going to get the number called 4.02 cubic meter per day. The biogas generation rate is larger as it also contains CO2, hydrogen sulfide. At that rate is going to be 5.03 cubic meter per day. Okay, it's a biogas. We're not talking about methane, right? It's everything. So it's going to increase. Okay, we're calculating the additional gas in there. Okay, the next slide. So the now we already calculated how much biogas, how much methane is produced. Now we are going to introduce this sulfate. If there is sulfate in your waste stream, now sulfur reducing bacteria are going to compete for the same substrate. Let's calculate how much methane it will produce in this scenario. Okay, So when the waste contains sulfate, part of the COD is diverted to sulfate reduction, and thus total COD available for methane production will be reduced greatly. Okay, so equation here is organic matter plus nutrient from sulfate. You produce hydrogen sulfide, water, carbonate, and new biomass. That's sulfur reducing bacteria is this biomass for this particular reaction. So theoretically, 1 gram COD is required for reduction of 1.5 gram sulfate. Okay, that's theory. Okay, if in this problem there is 2 gram per liter of sulfate, right? So the total COD consumed in sulfur reduction is 1.33 gram equal to 1330 milligrams, so converting to milligram. So COD available for methane production is 7,000 milligram is your total COD minus 1330. This is what's available for methanogenic bacteria. The rest is used by sulfur reducing bacteria. Okay, so we are now accounting for the 2 gram of sulfate. We're going to consume 1330 milligram of COD, and how much COD left for the methanogenic bacteria is 5670 milligrams per liter. Okay. Yeah. That's the problem. If you look at the problem, the COD in your waste is 7,000. Yeah, I will give you that whole thing to you later. Okay. If you read the problem, that's where the carbon is there. That's the 7,000 number. Okay. If you want to put the problem again, put the problem again. Go back a couple of more slides. Yeah, if you read that, that's your COD concentration. This is your sulfate in your stream, and we are explaining 10% is going to biomass production. Okay, so we're taking that input from there. That's where the 7,000 come from. Okay, all right. All right. So the next, this slide. Okay, here now we are inputting sulfate, and next slide. So when you take that, accounting for sulfur reducing bacterial use, this is what's available for methanogens, okay, out of 7,000. Okay, next one. So now you recalculate the same figure. Instead of 7,000, you put that 56.6 milligram input, and you are going to have 11.33 kilogram per day of methane produced by this COD available for methanogenic bacteria. Then again, it go back from equation 3 in example 1. Like keep it there. And go next one. So if you go back and look at from example from N, we have 1 kilogram COD going to produce this. We already figured that out, 0.35 cubic meter. So you multiply by 11.33 by 0.35. So you produce 3.97 cubic meter methane at standard temperature and pressure. Now for 20 degree centigrade operation temperature, you calculate that 293 divided by 273, you get 4.3 cubic meter per day. If there is sulfate in your system, your methane going to go down, right? Because bacteria competing. So that's going to be your theoretical methane yield and that scenario. So you have so much carbon coming in, so much efficiency, 85% COD removal, 10% going to biomass, the rest going to be methanogen. And the methane generation rate when sulfate is present is 4.3 cubic meter per day. Okay, the presence of sulfate reduced methane yield about 19%. Our total biogas will now contain more hydrogen sulfide, H2S, because of sulfate reducing bacteria producing H2S. That's going to be in the mixture of biogas now. Okay, H2S is again is going to go with your biogas. Okay, adding volume. Okay, okay, it look like a little more complicated, but that's how you solve the problem. Okay, so I gave you two scenarios. If you want me to repeat that again, we'll go back and repeat if you don't get anything. Yeah. Methane is reduced, but yeah, overall volume of methane is increased because the hydrogen sulfide, yeah, H2S gas in there, yeah, because that's now we call biogas. It's a mixture of H2S, CO2, and methane. Yeah, that's right. That's what it is in there. Okay. Right? Any other questions? Do I have another problem there or no? In there, do I have another problem or no? At the end of the problem, go down one more. Nothing. I thought I had one more problem. The PowerPoint has no more. Huh? I thought I had one more problem. I had a problem. Maybe tomorrow I will put in there. That problem is how to calculate your loading rate, solid loading rate, COD loading rate, how to calculate your HRT, SRT, right? I had a problem set. It's not there. Is it not moving or is it there or is it not there? I don't know where that problem went. I had a maybe that's end in here. I'll bring that tomorrow. We can recalculate how to calculate your loading rate for your organic loading rate, solid loading rate, all that. We'll talk about tomorrow. Okay. I thought I had problem, but I don't know what happened to that problem. So what we do, we'll talk about that question tomorrow, and then I'll give you guys a couple of scenarios. You can work in groups, okay, and come try to solve the problem. Okay, maybe we break into 3 groups, and Zoom people have to do it on their own. Okay, so if they have any questions in the Zoom. They can type.
The audience side,
They can type it in there. You can ask them
you can
to.
type it in the chat box.
Yeah. Yeah. It's included in, yeah, you're calculating for that's why the input of COD is less, not 7,000. It's 5,300 something. We took that COD out. In the presence of sulfate, because your methane is not going to be produced because they're competing. That's why we took out the input of COD for methane production is not 7,000. It's 5,000 something. 7,000 minus 1330, we took it out. Okay? Yeah. Yeah. This is soluble COD. Yeah, not all COD. Yeah. This is the carbon that is dissolved in the liquid. It's not the biomass. Total COD include all the microbes in there. We are not taking that. It's soluble COD. Yeah. I think I'm done it quicker than I thought. My third problem disappeared, so I will bring it tomorrow. Okay. I think you guys have more free time, so we'll give you a scenario tomorrow to work out. Okay. All right.
Thank you, sir, for providing invaluable and making the sessions more valuable, sir.
All right. Thank you. Thank you. Thank you so much. All right.
So tomorrow also it's the same time, 9:30. So all of you be in that class.